part C. Again, just performing the same steps we've been doing for parts A and B. The first thing I want to do is find my derivative. So I'll find h prime of x, quotient rule, so bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay, and just seeing if we can clean this up a little bit. I'm not sure if we really can. Let's see, there in the top we'll get 9x to the fourth plus 3x squared minus 6x to the fourth, all over that denominator. And I guess we can combine some like terms if we want to. So 3x to the fourth plus 3x squared over our denominator. Okay, to test for the critical points, we want to set our derivative equal to 0. And just notice that real quick, because we finally have a potential, our derivative, our first derivative is actually in a fraction, we can answer that whole question of when is the derivative equal to 0 and when is the derivative undefined. Because now it's a fraction, remember the only thing we can't ever have 0 in the denominator. So if I look here at the denominator, it's just 3x squared plus 1, all that squared. We want to determine what values of x would make that denominator go to 0. Okay. And then again, to figure out when the actual derivative equals 0, that's when we're going to test the top. So let's just test the top first. That looks a little bit easier. Okay, 3x to the fourth plus 3x squared equals 0. If I factor out, obviously, the common 3x squared, that leaves me with x squared plus 1. Okay. So 3x squared equals 0. X squared plus 1 equals 0. Nothing's going to come from that because x squared equals negative 1, and can't take a square root of a negative number and graph it technically. Can't graph imaginaries. And then this is telling us x equals 0. So it looks like we got a critical point at x equals 0. Okay. Let's see if we can get anything else from the denominator. What value of x is going to make this denominator go to 0? Well, we can kind of look at it real quick. What's given me a big hint that there might not be a whole lot is the fact that we're going to be squaring it several times for one thing. Okay, so if it's negative, we're going to square it on the inside. And square it, I mean, just think about it. Whether it's negative in here, we're just going to square become positive. And a positive times 3, and then add on another one and square it. It's definitely not going to be 0. Okay, or we can sit here and just even test it. We can say, okay, I don't want my denominator to equal 0, so let's finish solving it. You would take a square root of both sides, okay, and say 3x squared plus 1 cannot equal 0, and then by the time you move this around, it's saying x squared cannot equal a negative 1/3. You would go about taking a square root, and again, we have to throw this all out because it's going to be an imaginary number. So what we have just decided was the fact that our only critical point for this whole system is going to be at x equals 0. Okay, so now let's go up there back to our derivative. Let's use our sign chart and see about how we're going to, whether it's increasing and decreasing and all that with respect to 0. It's going to be pretty simple. Just have 0 on there. Oops. H prime of x. So to the left of 0, let's say is negative 1. Okay, let's go to our derivative function right here. Negative 1 to the fourth power, negative 1 squared, all of that up top is always going to be positive. Down here in the denominator, no matter what's in the space, I don't care what it comes out to, because I'm squaring, it's always positive. So it's always going to be positive right there. Okay. Let's think if we test a number to the right of 0. Let's say even 5. 5 to the fourth is positive, 5 squared is positive, especially if you multiply them by 3 and add, they're still going to be positive. Down here, who cares what the base is going to be? I'm always squaring it, so again, it's positive. So positive divided by positive is going to be a positive. All right, so what we have just found is that h of x is increasing on or for negative infinity to positive infinity. It's always increasing because our derivative is telling us it's always increasing. And because of that, I mean, I guess if you want to technically break it up, what we really could say, if we want to get a little more, I guess, technical, and this would be good to probably even write it like that. Let's say it's actually increasing from negative infinity to 0, and then from 0 to positive infinity. Because remember, right at 0, my derivative is actually equal to 0, so my graph is flat. It's like it's coming up at x equals 0, it goes flat for just one split second. And so if you're flat, you really technically can't be increasing or decreasing. And then it keeps going from there. So why don't we use this as our actual intervals of increasing right there, okay? And then because of that, we don't really have, there are no local max or mins. Because I have an, it's always going to be positive. It's never going to change from positive to negative or negative to positive. Okay.